So today we're very happy and excited to present to you our webinar via QUALITROL, overview of transformer monitoring. It is being presented by Emilio Morales. He is a technical application specialist here at QUALITROL. He has over 30 years experience in the design of power transformers in the transformer manufacturing industry. He's a member of the IEEE PS Transformer Committee, and is very active in participating in various task forces surrounding the industry. So without further ado, I will hand it over to Emilio, who will present this morning's session.
Good morning, everybody. Pleasure to be with you. We'll be talking, as Brian said, about transformer monitoring. Well, let's start then. This is the agenda. We're going to talk about why transformer monitoring is important, main transformer components, failure mechanisms, and measure signals, monitor parameters, and online monitoring systems in a very brief way. And then at the end, we'll finish with a session of questions. Well, let's start saying that online monitoring of power transformers and associated accessories is becoming an essential feature of electric utility systems. So therefore, we can say that loss of a transformer in a utility generation plant or process can cost many millions of dollars, depending on how critical is the transformer and how long it is out of service. Online monitoring and diagnostics is a useful tool to help operators to manage their assets and make decisions on continuing operation, maintenance, or replacement. One of the purposes of an online monitoring system is to prevent catastrophic failures and convert them into failures that will be repaired at a reduced cost during a planned outage. On this area, let's talk a little bit about, about the breakdown of failure probability. Let's assume that the transformer failure rate is applicable for major faults on the transformer. Major fault is usually understood as a fault leading to a removal of the unit from its base or a sign intervention on the active parts. Typical failure rates range between 0.5% for very reliable equipment to 3% for the very problematic. In this example, that is actually taken from the IEEE standard C57143, we're going to be using 1%. The catastrophic transformer failure rate is the proportion also of failures causing fire or a tank rupture with probable damage to peripheral equipment. This rate is usually very low, but since the results of a catastrophic failure are usually high in terms of cost and safety, it should be considered also. A figure of 1% of the transformer failure rate is used. So now we can say that this 1% of this number will be catastrophic failure. So we're talking about per unit will be 0.0001. Now, some of these faults of this 1% are detectable with existing means, such as gas accumulation relays, book coils relays, top oil temperature indicators, and hotspot simulators. All these equipment can provide warning to developing faults. Also, periodic inspection and oil sampling for DGA analysis is known to be an efficient monitoring procedure. Therefore, we can say that the proportion of faults that can be detected by these means can be estimated to be 30%. So by doing that, out of this 1%, 30% of that can be detected with existing means. Now, let's focus on the other part, the remaining faults that are not detectable with existing means. This portion is therefore estimated here to be 70% of all major faults. Some of these faults may display precursory signs, but these signs are too tenuous to be detected by existing devices. This is a type of fault that is targeted by online monitoring. Now, the detection efficiency can vary depending on the type of the monitoring system deployed. It would be unrealistic to expect a detection efficiency of 100%. Some faults then can go undetected or develop over a rate too fast to allow for proper alarming and orderly removal from service. So we're going to use in this example a detection efficiency of 60%. So 40% will go still undetected. Now, if we focus now on the 60%, and we talk about the non-catastrophic failures, which are defined here as the major failures contained with the transformer tank. While catastrophic failures are those involved in tank rupture, eventually fire with collateral damage to nearby equipment. It is useful to distinguish between these two failure modes since the economic consequences are quite different. So again, as we talked in the beginning, at this point, it is assumed here that a catastrophic failure accounts for 1% of total failures. So what we can take out of this figure, we can say that out of these detectable with existing means, 1% of this will be catastrophic failures that will be avoided without any extra monitoring system. Now, from this 70%, we can say that this number, which is basically 0.0042%, will be avoided by using non-detectable existing, with adding monitoring system. So out of this 1%, we will be, by existing means and monitoring equipment, we can get out of 0.72% of that 1% of catastrophic failures being detected and converting to catastrophic and non-catastrophic failures. So the improvement by using this monitoring system reduces a lot this rate. Now, let's talk about what kind of problems could be presented in the transformer. Transformer problems can be characterized as those that arise from manufacturing defects, those coming from deterioration processes, and those induced by operating conditions that exceed the capability of the transformer. These conditions might take many years to develop into a problem or failure. However, in some cases, undesirable consequences might develop rapidly. Some premature actions could result in wasted valuable maintenance resources if there is a problem or we believe there is a problem, but a late action could result in costly consequences. So using continuous monitoring will permit timely remedial actions, saving a lot of time or even avoiding some failures. Continuous monitoring also allows for higher loading, as continuous automated evaluation might alert users of conditions that could result in failure or excessive aging of critical insulation structures or transformer components. At the same time, degradation processes and operating conditions also play a significant role in premature failure of transformer ancillary components. Such items include bushings, lobe tap changers, and de-energized tap changers. But for this time, we will focus only on those items monitoring the main tank transformer or active part. We will talk about bushings, lobe tap changers, and other equipment in another session. Now, this also is presented in the ANSI standard C57143, and it talks about the different monitor components, failure mechanisms, and measured signals. If we talk about, I'm sorry about that. Among the parts that we have in a transformer, some of the components will be the magnetic circuit. Magnetic circuit is composed of leg, yokes. There is a core ground lead, and sometimes there is a magnetic shield. The phenomenon leading to failure in this particular case will be overheating of laminations and over core joints. And the measured signal will be either top and bottom temperatures, ambient temperatures, excitation currents, hydrogen or multi-gas, gas accumulation relay, infrared scan. And the diagnostic interpretation can be done using the temperature analysis, PD model, or gas analysis. Another thing will be like a core ground and magnetic shield. So the loss of core ground or unintentional core and shield grounds create problems in discharges. This could be detected by measuring hydrogen or multi-gas, gas accumulation relay, core hotspots, acoustical and electrical PD or infrared scan. In the mode of interpretation diagnostic will be a gas analysis or PD mode. We have the same for winding insulation, and we can talk here about phase-to-phase, winding to winding, winding to ground, and minor insulation could be turn to turn, layer to layer, this to this, depending on the design. And the phenomenon leading to failure will be bubble generation, overloading of transformers, partial discharge. And these are the signals that can be measured to be able to detect these problems. I'm going to just mention some of them: winding temperature, electrical PD, acoustic PD, line currents, moisture in oil temperature, and most of them are common. And in other words, you can see that for bubble generation, one of the signals measured will be winding temperature. It will be the same thing for overloading of the transformer. So it doesn't mean that you have to repeat all those measured signals. In the diagnostic interpretation, in this particular case for bubble generation, will be moisture and thermal models, gas models. For overloading of the transformer will be moisture and thermal model. For PD, it will be gas analysis and PD analysis. Now, for the liquid insulation, we will have the same phenomena leading to failure will be moisture contamination, arcing, or partial discharge. So again, a way to detect that will be to measure top and bottom temperatures, ambient temperature, moisture in oil. On arcing, it will be hydrogen, acetylene, or we can check on the gas accumulation relay. For PD, it will be hydrogen or multi-gas, gas accumulation relay, acoustical, electrical PD. As you can see, they repeat themselves. So using the same measure signals, you will be able to detect several type of phenomena leading to failure. The same apply for the cooling system, pumps or pumps. The phenomena will be electrical failures of pumps and fans, or mechanical failure. Now, how can we detect those? By measuring the current of the motors for the fan and pumps, flow of oil. That way we can tell that the pump has a problem. Top oil temperature, winding temperature, dissolved gas in oil, bearing wear detector for units having pumps, standard mechanical vibration, infrared scan, ambient temperature. And we also have a diagnostic interpretation, which would be a thermal model, gas analysis, or pumps and fans model. Cooling control, we can check failure or inaccuracy of temperature sensors, pump and fans running in reverse by measuring ambient temperature, top oil temperature, winding temperature, load current, cooling control voltage, cooling supply voltage. Radiators and coolers, the phenomenon will be internal or external blocking of radiators resulting in poor heat exchange. So basically, by measuring top and bottom oil temperature will be the main measure signal. And in the tank, gasket and well seams will be the component. Oil level drops exposing the winding moisture contamination will be the phenomenon. And we can detect this by measuring the oil level or the nitrogen pressure. Now, let's talk about monitor parameters. One of the more important is DGA. Online monitoring of individual gases is much more revealing than periodic DGA. A single gas, in this case let's talk about hydrogen, and multiple gas monitors provide early warning detection and varying degrees of additional diagnostic benefits. There is a secret recommendation for to install hydrogen monitors on healthy transformers and multi-gas monitors and critical or already gassing transformers. Give me a second. So, online hydrogen monitors are useful for detecting rapidly and slowly developing faults. So an approach could be to install online hydrogen monitors on new or healthy transformer at a much lower price than when alarm actuates at a sample can be drawn and sent to a laboratory for a complemented DGA. So using a hydrogen monitor, we can check on rate of change and concentration levels. So there is the point where you have to make a decision on which way would be the best to do, if using a single gas or a multiple gas. When somebody asks me about it, I say, what is the point of monitoring a healthy transformer with a multi-gas system and do all the maintenance, the cost of the equipment, when you can use a very simple one? Once you get an alarm, you can take the a sample, send it to a lab, and check what comes out. Depending on that analysis, you can take the decision then to use a more complex system like a multi-gas system to keep a very close surveillance of the transformer if it is a critical unit, and be aware when that unit needs to be changed. Another monitoring parameter will be partial discharge. The detection can be performed using radio frequency and acoustic techniques. Among radio frequency, you can use electric sensors or ultra high frequency sensors. For the acoustic techniques, you need to use acoustic sensors. Now, what is the benefit of having a partial discharge monitoring? There are some type of faults that will develop so rapidly that even the DGA online won't be able to detect it. I know at least of 2-3 cases where a transformer failed right after a DGA was taken, and the DGA showed to be okay. If those units would had a PD monitor, the user will know that there was a problem and will be able to do something. Among those 3 cases that I know, 2 of those, if they had this PD monitor, would have been able to save the transformer, because the type of failure that ended up rupturing the tank was a very simple one that could have been repaired on site, saving a lot of money and a lot of downtime. Now, let's say that you already find out that you have, or you already detected PD inside of the transformer. What would be the next step to get the whole benefit out of the PD monitoring? Well, if you have more than one sensor, let's say a minimum of 3, you can do also the location of the problem. The benefit would be that if you are able to locate the problem and it's outside of the current core assembly, then you can decide to lower the oil, make an inspection, and it might be a very simple problem to solve in the field. And if that's so, it will save a lot of money and a lot of downtime. So for this application of location, only ultra-high frequency sensors and acoustic sensors can be used. Benefit of ultra-high frequency sensors over acoustic sensors is that they can mitigate the noise very well and are even able to do detection of problems within the windings. Acoustic sensors, the benefit is that they are not intrusive in the transformer. They can be mounted outside, but they are more prone to external noise. In any case, to me, if you're going to do PD monitoring, it would be worth to use at least 3 or more PD sensors. So if you detect the problem, then you can go and do a location and maybe even save the unit. Now, let's talk about temperatures. Temperatures are used by the majority of monitoring systems to indicate the instantaneous thermal rating of the transformer and to infer the health of cooling systems. Among those temperatures that are normally measured will be the top oil, bottom oil, winding hotspot, ambient temperature, cooler inlet oil, cooler outlet oil, and lately you can use also the car hotspot. Generally, a winding temperature indication is required for each winding if a tap changer is fitted on the transformer or it has more than 2 windings. The winding hotspot temperature might be derived by a monitoring system using the oil temperature and load data, or by direct measurement of the winding hotspot temperature using fiber optic techniques. Direct hotspot measurement is viable by determining the thermal parameter of a transformer. Therefore, it's quite critical to have an accuracy of the temperatures measured. Among this temperature, top oil, bottom oil, cooler outlet, cooler inlet, and cooling medium of inlet to coolers, the ambient temperature, it's a very simple probe that can be used, and it will be relatively accurate. The winding hotspot is not the same. It has other issues. Most of the cases, the winding hotspot is based on the gradient from the winding to the oil, and is based either on calculations or using a factor. But it can never be, sorry about that. It won't be using a thermal image system. You won't be able to measure it directly. The only way that it can be measured directly is basically using direct measurement or using fiber optics. With fiber optics, the problem is to know the location of the probe. People might think that it will be in the top disk, but recent papers have shown that it could be between the first, second, or third top disk. Why is that? Leakage flux at the ends increases the losses in the conductor of the windings, so losses are higher in the top and bottom. But the top is in contact with the hotter oil, so it should normally be on top of the HV winding or any winding. Now, you may know already that the life of the transformer is based on a continuous operation at 110 degrees C hotspot for 65 degrees C rise insulation. Well, if that number cannot be measured accurately, in the unit, let's say, is running at 110 degrees C, for every 6 or 7 degrees C, you will reduce the life of the transformer to half. So there are different criteria. So let's say the criteria is 20 years of life. And if a unit is running at 110, it will last the 20 years. But if a unit is running at 116 degrees, it will last 10 years. The same applies the other way around. If the unit is working at 104, 103 degrees C, the unit may end up lasting twice as much. So instead of 20, it could be 40. So monitoring the temperatures will give us a very good tool to extend the life of the transformer. The other one, the core hotspot, the only way, the way I know that it's being measured is using fiber optics. So a recommendation will be, if you have already decided to use fiber optics, add another probe to measure the hotspot of the core, which will be normally in this area where the leakage flux of the windings will be hitting it perpendicular. Another monitor parameter is the moisture in oil. Moisture in oil can give us an idea of what the moisture is in the oil. The problem is that to be able to do that correlation, conditions in the transformer have to be very stable, and that's the only way that you can get an assessment or an accurate assessment of the moisture in the insulation. But we know that transformers never are in a steady condition. The only way that they can be is they are de-energized, and the ambient temperature is quite average. I mean, it's not changing too much. And that way you can, with the unit oil fillet, you can make a guess of what the moisture in insulation would be. This is a factor that is normally not considered when somebody is doing an analysis of age of the insulation or life extension. And the reason is because it's very difficult to find out how much insulation is really in the insulation, how much moisture is in the insulation. And what is this? Well, first, let's see how that affects the effect of moisture and the aging of the transformer is similar to temperature. If a transformer is considered to be dry, if it is, let's say, 0.5% of moisture in the insulation, if that's the case, you can get a aging factor due to the moisture in the insulation of 1. But if you get 1%, you will get an aging factor of 2. So the problem with that is that that the transformer is moisture in the transformer is always present. That moisture will come from manufacturing, the moisture residual from manufacturing, moisture ingress from environment, and moisture produced by aging of cellulose. So moisture is critical for insulation life and insulation assessment, but it's not a direct measurement. So in this case, we can see that the moisture in the insulation is assessed by measuring the moisture in the oil. Another problem with this is that where you want to know where the moisture is in the hot spot of the winding. And even if you can relate to how much moisture is in the insulation, what you want to know is how much moisture is in the hot spot of the winding. So it's always a difficult process. And my recommendation is when you get a unit, you can be expected, that unit is expected to be dry. So at that point in time, if you order the unit with a moisture in oil detector, you can assume that unit is dry, and you can get a fingerprint and the different conditions loading. And once those parameters change, you can relate that the unit has moisture. And as the moisture affects so much the insulation, it's better to take action and dry out the unit. Another parameter will be low current and voltage. The low current will give means to gauge the thermal performance. It's normally an input for any monitor any electronic monitor, and it can give us also it can be used for cooler efficiency monitoring. As we talked before, if you have more than 2 windings or you have a low tap changer, measurement is required for each winding because the currents will be different. Another parameter is the monitoring of the cooler operation. As we talked a little bit before, the pump and fan contactors are required to be provided with auxiliary contact. Flow gauge is a very wear detector to monitor the pump operation, and the monitoring of the current of the pumps and fans is required. So any change could lead us to find out that there is a problem with the cooler operation. It's not recommended anyway to measure individual fans or individual pumps because you can group them, and once you find a difference, you can then go and look for the specific one that is giving problems. Cooling control and supply voltage are very helpful to find out if there are problems in the supply of this, and maybe leading to a problem with the control cooling. Another item that is important to monitor will be the conservator tank bladder. The rupture of the bladder in the oil preservation system can be useful to prevent the ingress of moisture in the oil. There are systems of monitors that are placed inside of the bladder, but there are another ones that can be used very simple. One would be to add a small tank welded to the conservator tank to the top on one side of the conservator tank with two holes, one at the top, one on the bottom, and put a regular oil level indicator there. So if by any chance the bladder ruptures, air will come into the conservator tank and go into the top. Oil will go inside of the bladder. So in this small compartment that is connected to the conservator tank, air will get inside that, and the oil level inside of that chamber will drop, and the oil level indicator will be able to detect this change, and indicating that there is a problem with the bladder in a very simple way. This is the oil level. They recommended that to monitor all of them and all the separated oil filler compartments for detecting leaks. And in cases of transformer having a book close relay, it can prevent an unexpected operation due to the low oil level. Another monitoring parameter would be the rate of full gas production. It provides information about the development of a fault. In any case, the safety of continuing uses of a transformer by this condition has to be carefully evaluated. The way that you can monitor this is if you have a book close relay or a gas accumulation relay. The gas accumulation relay can be provided with a potentiometer, so you can connect that directly to the system and detect a change of rate. The very useful application of this is if you have DGA. Again, DGA might take some time to be able to detect a problem because of the gas combining with the oil and traveling within the transformer. It might take, therefore, some time for the DGA monitor to detect it. But if you have one of these two, a book coils or a gas relay, and you're monitoring them, a bubble might travel faster and give you an indication of an incipient problem, and you can get close to the transformer or get a close surveillance to avoid problems, bigger problems. Another monitored parameter will be pressure. This can be very helpful to detect any abnormal condition. On transformer with book coils, with conservator tank, it can give you an indication that the breathing system of the preservation system is blocked, and an action can be taken before it gets worse. A transformer with nitrogen system, it will be measuring or monitoring the normal operation of the nitrogen system inner tire, and if there is you can get a fingerprint of that operation, and if that changes, then you can take an inspection and find out what's going on with that system. There might be some faults that will develop very slowly, but will be maybe releasing some energy that will make an increase of the pressure faster than what the nitrogen system will do when it detects a lower pressure, and can give you an indication of something is not normal. Another monitoring parameter will be monitoring the core ground current, which will be an indication of faults or circulating currents. In this case, it's recommended to specify that the core and frame ground connection to be brought out and connected to ground on the cover. And right there, you can use a CT and connect it to a monitor to detect any change on the circulating and the current going to ground, or if a huge increase will tell you that there is a undesired connection to ground. This is a recent one. In high latitudes, you can get a geomagnetic induced current that we will be inducing in Earth and then come out through the neutral of the transformers and then into the transmission lines. These currents will tend to saturate the core depending on the magnitude, but it doesn't require much to get the core saturated. And once it gets saturated, the flux will go out of the core and will start hitting internal parts, components of the transformer. At the same time, this GIC current will make an increase on the excitation current of the transformer. So a very high current can circulate in the windings and overheat them. So if you monitor the current on the neutral, it will give you an indication as to the cause of the agnostic gases or other fault conditions. In other words, you can relate to the measurement of this GIC current to gassing events, for example, and if the gas stops after some hours after the event of the GIC, then you can say, well, I think this is normal, and transformer didn't suffer any problem. But if that condition continues, it can tell you that the GIC was the one that started a problem inside of the transformer. Transformers are supposed to withstand these currents because they don't last too much, and is a very small part of the RMS value. So effectively, it's even if it is a very high current, the RMS value is quite not that much. So transformer should be able to handle these GIC currents as an overloading condition. But it's always good to monitor them and to be able to correlate them, and mainly with a gas monitor. Now, let's talk about online monitoring systems. Transformers online monitoring equipment can vary depending on the number of parameters that are monitored and the desired accessibility of the data. There are sophisticated online monitoring systems that can monitor many parameters simultaneously. The systems can be integrated into a complete substation system. And they consist of sensors, indication, electronic hardware interconnection, communication interface, and data processing. Sensors measure electrical, chemical, and physical processes and convert them into measurements to physical signals. The type of output signal needs to be compatible with the receiving electronic hardware. For this particular, the sensors need to, we need to be aware of noise and ways to eliminate it. The indication is displayed of the monitored information. It can be available at the transformer, on the control room, and on remote sites. The electronic hardware may be described as a remote terminal, RTU, a data acquisition unit, or a PLC, or an IED, or similar. The transfer of information from the transformer to the control room and on to the main consolidated information location can be achieved using various hardware interconnection methods. Common methods interconnection include RS-232, RS-48, fiber optics, Ethernet, radio frequency, and broadband over power line. The communication interface can be industry standard protocols such as DMP-3, Modbus, IC61850, and IC60870. The data processing is, and all acquired data need processing in some form. So sometimes the data could be used in the form in which they are acquired, but other ones need to be processed further. Now, what would be the selection criterion for online monitoring systems? These are normally based on the priorities of the transformer owner. The operation, reliability, and cost are the main priorities of these ones. And therefore, a methodology needs to take into account many factors, which the most important ones would be the analysis of current operating cost and risk, and the consequences versus expected benefits. a decision can be made of the need costs of online monitoring and offline monitoring requirements. Now, this can look too great at this point, but if you look at the 57, the standard IEEE C57 143, this standard has a very good example on how to do this, and is very practical. There are just a few numbers, a few variables that are depending on the transformer itself and the utility that is doing the analysis. But it's very simple. I had found that a lot of people is looking to ways to justify the monitoring systems with their bosses or the management, and sometimes it's very difficult because there is not a base or not a thing. Or they don't know about there is an existing method to do it. So I recommend you, if you are in this situation, to take this standard. Again, it's C57-143. Look at the method that is there, and you can apply directly to your own needs and justify the monitoring equipment that you need. This is the last slide. Hope this is it was something good for you. And if you have, anything for me, let me know.
Thank you very much, Emilio. So this is Brian again, and we are now in the question and answer part of the presentation. I do want to let everyone know that we have been recording this since the beginning, and everyone that has registered for this event will get a link by the end of the week with a link to this recorded session. So you'll be able to see the slides and pause the presentation at any time and listen to Emilio's audio, and at your leisure. Now, when it comes to questions, we would like to have people type their questions into the chat window on the right. It's the CHAT. That's the only window we're going to be looking at. So if you would, you can type in your questions there. We will try to get to as many as possible. We do have a lot of people online, so I'll be reading off the questions. Emilio will be answering them verbally. So one of the quick question someone had was, what does GIC stand for?
GIC stands for geomagnetic induced currents. Basically, give me a second. There are a phenomenon, solar storms, obviously coming from the sun, and there are contain a variable flow of charged particles from corona mass ejection, obviously again from the sun, to the Earth's atmosphere, and those are effectively high electric currents in the ionosphere, call it electrojet. This current can be reach several million amps during a geomagnetic storm. As this current varies, it induces a voltage potential on the surface of the air of up to 6 volts per kilometer. This voltage causes geomagnetic induced currents, and they normally will flow into the system via a transformer at a start point on the neutral. Will travel to the transmission line, get to another transformer that has a Y star connection, and get back into the ground and close the loop. So that's what it is. It's a phenomenon that normally takes, it's cyclical, and it gets peak value every 11 years. And for your information, 2013 is cycle number 24, and we are already detecting on some transformers these GIC currents.
Okay. So what will be the maximum length of signal cables that can be used between transformer and online monitoring system?
Well, it all depends if it is copper or fiber optic. With copper, it can be much. It will have to be quite close. It could be maybe 60 meters. But with fiber optics, it can be up to 1,200 meters.
Okay. And I'm going to roll through some of these questions pretty quickly because I'm getting a lot, so I'm going to try to get to as many as possible and still respect the time of about 12 minutes left. So how is the GIC current detected in the transformer neutral, with a shunt or a CT?
No, it's not a CT or shunt. We use Hall effect sensor. Hall effect sensor is using a different technique, and the good thing about it is they can detect DC and AC as well, but it's not a shunt or a CT.
Okay. Why use UHF as opposed to VHF-AM to detect arcing? I'm assuming that this is why the UHF receiver.
Yeah, the benefit of using UHF is because the noise tend to decrement. There is another word, I can't remember what is the word now. The amplitude tend to decrease over the range of frequency, and at a higher frequencies, the PD is still there. So that's how, I mean, if you remember, I mentioned that ultra high frequency was much better because of it wasn't affected as much as acoustic by external noise. And the reason is because the external noise won't be present at those as much as those higher frequencies.
Okay. Can you comment a little more on the type of sensors that are utilized? Can a partial discharge, a dissolved gas, and moisture sensor all be utilized at the same time?
Okay, let me see what we're talking here about. Okay, we talk about. Could you repeat just the question just to get to the? I think one was the DGA, isn't it?
Yeah, so basically it's can a partial discharge, dissolved gas, and moisture sensor all be utilized at the same time?
The question is if they are utilized at the same time.
Mm-hmm.
Is that correct?
Yeah.
Okay, we're talking about DGA, PD, you say also temperature?
And moisture.
And moisture. Let's say DGA and PD. It's not like a competition. It's more like they complement each other. And while the PD will let you know that you have a partial discharge problem, the DGA will tell you either is a it's a partial discharge or a different type of problem. So they complement from that point of view that they will confirm the type of fault that you're having. But mainly PD the main advantage is that it can be able to detect those problems much faster rate than DGA in case the incipient problem is evolving much faster. The idea of having all of them together is to be able to have the different inputs to the algorithm and therefore confirm more accurately the type of fault or the type of problem, or that there is actually a problem. So they basically complement each other to confirm the type of problem or that there is actually a problem.
Okay.
If we go a little bit more deeper on moisture and temperature, we talked that the age on or life of the insulation is affected almost equally by temperature and moisture. So you need those two factors in the algorithm of life calculation to get an accurate data.
Okay. Another question we got is the online monitoring system located on the protection control panels inside a substation?
It can be either way. It can be inside of the control cabinet of the transformer. It can be mounted outside of the control cabinet of the transformer. It can be mounted on a pedestal in the middle of the substation, or it can go all the way to the substation room.
Okay. Can this equipment be applied for converter transformers in an HVDC application?
Yes, most of these monitored parameters are applicable to HVDC.
Okay.
May I just say something? There's some
Sure.
things that need to be into consideration. One of them being fiber optics, but otherwise everything else more likely will be the same.
Okay. Another question. As I understand it, in regards of DGA, it's your recommendation to perform multiple gas analysis on older transformers rather than in newer ones, correct?
Yes.
Okay.
Yes, and the reason being is when you receive a unit, and let's say it doesn't have no online monitoring for DGA, the normal practice will be anyway on the first year maybe take some samples a monthly basis, then every 3 months, and then every 6 months, within a year. And that would be just to confirm that transformer is healthy, it doesn't have any problem. And now after that, normally, I don't mean with this that that's the case always, but a sample might be drawn only once a year. Now, let's say that we have online monitoring. More likely, people will still do the same thing, even having an online system. It will take some samples at the beginning after the unit has been in place, and analyze those and confirm everything is working perfectly, including the monitoring system. Now, therefore, under those conditions, those units should be sound, meaning they shouldn't be generating any abnormal gases or amount of gases. So when I say under those conditions, you can have a very simple monitor, single gas monitor. Let's use an example, hydrogen. And what you're looking basically under those conditions is to have an alarm when something is going abnormal. And let's say in the same unit, you put in a multi-gas system. And it's a perfectly sound unit. And you're monitoring it with this complex system that requires, some of them require a lot of maintenance, calibrations. And you're spending a lot of money on a really sound unit. So the point is, if you have a hydrogen system, and once you get an alarm, you take a sample, if there is a problem, at that point in time, based on the criticality of the transformer, you can then decide to put a multi-gas system to have a very close surveillance on that unit to extend the life with no risk, or you get a replacement for that transformer.
Okay. What kinds of conditions cannot be detected by monitoring systems? I am referring to the 0.0028 number you had in one of the initial slides.
Okay, let me... Yes, let me, in a second. These are normally this non-detectable faults could be those, let's say, lighting. The unit has been in service for a lot of years. Insulation is still okay, but it's weak. And suddenly you have a lighting that a transformer is supposed to withstand, but due to the condition of its insulation, it will fail right away. So there's nothing that can be done at that point, even with monitoring system. Same will be applicable to a true fault. You have a fault in the secondary side of the transformer. The unit might be loose because the insulation has age and is shrinked, and now there is a lot of movement inside when there is a fault. And under those conditions, the unit might fail right away with no warning at all.
Okay. What is the response time for one DGA multi-gas monitor, two H2 monitors? An example, how long does it take to measure the ppm and report it to the user?
Okay. I'm not sure if the question would be from the point on time that the monitor is detecting the gas. If that's the case, I mean, it's right away. I mean, I guess the problem would be if there is an incipient fault. The time from that fault to be detected by the DGA, it could take days. But once the system, the online system, detects it, the warning is immediately to the user.
Okay. Faults in bushing. Does this equipment monitor that?
Sorry again. Could you repeat the question?
Faults in bushing.
Faults in bushing.
Yeah.
No. I mentioned at the beginning, not at the beginning of the presentation, but early stage of the presentation, that we will be concentrating on basically the main tank of the transformer, which contains the active part. Because bushings and LTCs, I mean, by themselves require another presentation. But anyway, PD will be able to detect problems on the bushings. You won't be able to say it is a bushing. You just know that there is a PD problem, but you might not know where it is. And that's where location is very helpful. So that's the problem. For a bushing, something very helpful would be to measure the power factor, continuous power factor. And that basically can tell you if the bushing is going bad. And my recommendation is, I mean, I didn't include it in this presentation, but if in the future when we do the presentation for this ancillary equipment, I will very strongly recommend to use monitoring the bushing with power factor or PD, because the problem is not that the bushing fails. It's in most cases when the bushing fails, it takes the transformer with it, and that is why it is very highly recommended to monitor the bushing as well.
Okay. I think we're going to have time for probably two more questions. So number one will be the online gas monitoring instrument shown. Does it only do H2 or multi-gas?
It only does H2.
Okay. And final question, online PD monitoring. Is there a criteria to assess the PD values?
Well, I talk about three different types. There are others, but those are the most common ones. The using radio frequency or electrical systems, and the most common one is the one that is connected to the tap of the transformer, to the tap of the bushings. It uses the same system that is used in the factory to check that the unit is PD-free or partial discharge-free, and it's measuring picocoulombs. Acoustic method or ultra-high frequency method use the different values. Ultra-high frequency use dBm, it doesn't use picocoulomb, and acoustic might be a similar way. Now, the way to assess these values is, first of all, when the transformer is tested on the factory, it's tested at 150% voltage. On site, the transformer is working at 100% voltage. So even if there is could be a picocoulomb direct measurement, I guess yes, you can relate it to picocoulombs. With acoustic and ultra high frequency, you basically use a fingerprint. When you put you have the unit on site, and if it's a new transformer, the transformer comes with the sensors already in place. you connect the unit, and you will assume that the unit is PD-free. There's a way to assume that, base it on if you do a DGA, even if you don't have a monitoring system online, you will get a sample for the first few months and define that the unit is PD-free by the gases that are being detected or not detected. So you use that as a fingerprint, and when time comes and you start detecting PD, you can basically check on how the rate is going, the trend, and assume that there is a problem. But right now, we QUALITROL, we're working on a project where we will try to be able to correlate picocoulombs with dBm. But at this point in time, it's only based on what the unit is without PD, and if with time it changes, and it can give you a warning based on that. On a unit that is already has PD, and let's say at that point in time the sensors are installed, you basically looking at the trend. If the trend changes rapidly, suddenly, then an action has to be taken.
Okay, well, thank you very much, Emilio, for this fantastic presentation. Thank you, everyone who attended. Again, look for an email with a link to this recording of the webinar. I apologize to anyone who didn't get their question answered directly. We had probably about, I would say, almost 40 questions posted to the chat window. We just unfortunately ran out of time. Thank you very much, and enjoy the rest of your day. Goodbye.